Hi there, my name is Ken. I'm a renewable energy student, passionate about science, technology, and all engineering related topics. In this channel, I break down all the complicated concepts that might be confusing in order to help you understand how they impact and shape today's world. So if you feel interested, consider subscribing so you don't miss any video. And in today's video, we uncover one of the most important concepts and key idea in the modern mathematics and physics. And this is the derivative. Let's assume we have a small ball on top of a curved surface, and we want to find out what will the ball do next. Will it go left, right, or just stay in the middle? Well, this just depends on one factor, the slope of the curve at that specific position. If the slope is 0, the ball will just stay in the middle. If it is positive, the ball will go one direction, and if it's negative, the bar will go another direction. Now you might ask yourself how to exactly know what is the slope of the curve at a specific point. If it's the case, just make sure to subscribe because that is exactly where the derivative comes in. When thinking about the concept of the derivative, there are different methods that can be taken. Let's observe this one. I've tried to represent a fictive function f here that represents the height of an object depending on the time. Let's assume we've turned the object and it just goes up, and at a specific moment it starts to fall down. And then something pushes up once again and then it goes up. So we have this curve that looks pretty like this. I've set the two instants t1 and t2 as the point where I want to assess how my system is generally behaving. For that purpose, I need to compare the difference between f2 and f1 to the difference between t1 and t2. So I can call it alpha, which will be of t2 minus f of t1 divided by t2 minus t1. So this difference divided by this other difference. That tells me how the system is generally behaving, if it's growing, it's falling, or if it's just 0. In our case, we can just see f2 is bigger than f1. That means this difference is positive. And also t2 is also bigger than t1. That also means the difference is also positive. And the quotient from both positive numbers will be positive. That means this number alpha will be bigger than 0. It comes out that alpha is bigger than 0, and since alpha is the slope of this function in the interval t1, t2, we can have as general conclusion that if you're here somewhere between t1 and t2, we can know that the height of the object we've been throwing up tends to go up, tends to grow. We don't have any information about if it has fallen somewhere before it goes up, or if it's just go this direction or there. We don't have any information, because if the graph of the function were also so or even so, we have become exactly the same general slope. In order to assess how the system is generally behaving when the time comes to t0, the time we've chosen to observe the system, we need to shrink this interval close enough to t0. For that purpose, we use exactly the same formula. We have here f of t minus f of t0 divided by the difference between t and t0. But instead of building a normal quotient, we will try to find out the limit of this quotient when t comes really close to t0. Here we are. This is the general definition of the derivative, and it actually tells us more information about how the function is behaving when it comes close to a specific point than the general average slope. Let us use this formula to find what is the derivative of some common functions. The formula is f prime x equals to the limit when x comes to x0 of fx minus fx0 divided by x minus x0. Let us take the first example. Fx plus 2x squared. We want to find out what is the derivative. The formula is f prime x will be the limit when x goes to x0 of x squared, which is fx in our case, minus x0 squared divided by x minus x0. That would be, here I use the third algebraic product that says that x squared minus x squared 0 would be x minus x0 times x plus x0. I divided it by x minus x0. Here it's the limit, forget about it. The limit when x goes to x0. So now these two can go away, and then I have the limit when x goes close to x0 of x plus x0. I can just replace x by x0 here, and then I'll have x plus x0. I mean x plus x0, which is 2 times x0. So as a result comes that the derivative of our function f, which is x squared, will be 2 times x. Here our second example. Fx equals to x to the power of 3. So f prime x will be the limit when x goes to x0 of fx, which is in our case x to the power of 3 minus x0 to the power of 3 divided by the difference. The factorization form is x minus x0 multiplied by x squared plus x times a0 plus x0 squared divided, okay, I forgot to write the limit. It's the limit for x times x0 divided by the difference, x minus x0. And here, once again, we can have these two expressions. Since they are the same, they can just go, and then we have the limit when x goes to x0 of x squared plus x times x0 plus x0 squared. This will be x0 squared plus x0 times x0 plus x0 squared. That will be 3 times x0 squared. That is f prime. If you've paid attention, you surely may have noticed something. As we are trying to be the derivative of x squared, we become fx equals to x squared, and the derivative was f prime x equals to 2 times x. Now we also build the derivative of x to the power of 3, and as a result we had f prime x equals to 3 times x squared. For polynomial function, the derivative can be expressed in one specific form. The function is in the form fx equals to a times x to the power of n. The derivative will be in the form f prime x equals to n times a times x to the power of n minus 1. That means the exponent always decreases by 1. Only the case for polynomial function, but there are also some patterns in trigonometrical function and also exponential function, but that will be the topic of another video. I honestly don't think that it's very complicated to find on the internet what are the general expression of the derivative of some normal functions like trigonometrical functions, polynomial functions, or even exponential functions. That is not a problem. But what sometimes fails is that explanation on what is the derivative, what it does, which information it gives, and that is exactly what I wanted to do in this video. And if you liked it, I highly recommend you to like, to hit the subscribe button so you don't miss any video. See you next time.